Good evening, everybody, to a very dramatic BrisScience opening. Sorry? Good evening. Thank you so much for responding. There is one polite person in the room tonight. I am your host for BrisScience, Joel Gilmore. Thank you all so much for coming out tonight. If this is your first night, this is a free public series of science held once a month here at the fantastic The Edge, as part of the State Library, and put together by the University of Queensland, who is our fantastic supporters and sponsors for a decade now. And we're very, very excited to be here tonight. I'd also like to start by acknowledging the traditional owners of the land on which we're meeting tonight and pay my respect to elders both past and present. And I also want to acknowledge the ongoing efforts to protect and promote Aboriginal and Torres Strait Islander culture and create a lasting legacy for elders past, present and future. So tonight we do have an incredible speaker who's going to talk about the secrets of the universe. Couple little bits of housekeeping first. If you've got a mobile phone, now is a great time to turn it to silent and to boot up Twitter and get ready to tweet your questions, comments, photos and so forth with the hashtag BrisScience throughout the night. You might have also seen a question sheet on the way in. If you have one of those or any other piece of paper, you can write down your questions on there. $50 notes will get special treatment if you mark it down on there. And at the end of the talk, there'll be some time to get through as many questions as we can. So through Twitter and those pieces of paper. And of course, afterwards, we do have food and drink outside, and we would love you to join us for that. And Sam will be available to answer lots and lots of questions there. He has nothing planned for the whole rest of the evening, so you can monopolise him as much as you like. Okay, I think that's all of the housekeeping for now. So I've already hinted, but tonight, our speaker is the fantastic Samuel Hinton, who is an award-winning astrophysicist, as well as robotics and software engineer, a cat enthusiast, an incredible science communicator, passionate about sharing science and space with the world, and a TV star. He recently competed on Survivor as a champions contestant. And, ooh, ominous, interesting. So tonight, though, he will be championing his fantastic work on dark energy and dark matter, at least some of the missing bits of the universe. And he'll be talking about his work on exploring that through exploding stars. So could you please put your hands together for our fantastic speaker tonight, Samuel Hinton.
Hey guys, if anyone hasn't seen this Survivor thing, spoiler alert, I lost real bad. I'm so sorry, Mum. Didn't mean it. So tonight I figure it's good to talk about the dark side of the universe. Before I jump into that, a brief, there we go, about who I am. So Samuel Hinton, the introduction's been done, so this gets to be a really short slide. I do lots of stuff, lots of projects in astrophysics. I'm going to be talking more about a general overview tonight, rather than delving into any of the technical details. But if there's any potential students out there that think, hey, maybe this sounds cool, I'll go into it. I've got a bunch of projects listed up here of things that you can do in astrophysics. So feel free to check that out if you want to know what it is we do day to day, rather than up on the stage when there's bright lights in your eyes. So what I'm talking about tonight is dark energy and dark matter, and the reason I'm talking about it is because of this diagram here, specifically the little fraction that says normal stuff. Normal stuff is baryonic matter, you, me, the chairs, the Earth, the sun, everything that we're familiar with, and it makes up that much of the universe, 5%. That's not much of the universe, and so what's the rest of it? Well, we have this big chunk up here called dark matter. So what is that? Well, I'll get to that a bit later, but it's essentially, at the most basic level, matter that doesn't interact with anything but gravity. As the name suggests, it's dark, that is no electromagnetism, no weak, no strong force, just gravity, so we can't really see it. And then to top that off, we have even more. 70% of the universe is dark energy, and that's even weirder because dark matter, we can sort of intuitively understand that. It's like normal matter, it just doesn't reflect light. You know, that's simple. Dark energy, you can think of that more like a mysterious anti-gravity force that permeates the entire universe, causing the expansion to accelerate. And there's not much that we can intuitively link that to, so it's much harder to actually talk about and investigate. So I've broken this talk into two little sections. The first of them is a history of the universe, because it's good to have context before I launch into the science, how we do the science, and why we care. And the second part is obviously the science itself. So starting that off, a brief history of the universe in hopefully around 20 minutes, so 14 billion years down to 20 minutes. I'm going to skip some things. I hope that's all right. All right, so time equals 0, the Big Bang. And if you Google image the Big Bang, like I have obviously done, you get hundreds of pictures like this, at some point exploding outwards. It's wrong. It's completely wrong, and it perpetuates the myth that the Big Bang was a point in space that then exploded and everything came about into it. The Big Bang was all of space. All of space compressed down to essentially size 0, and it all expanded. Unfortunately, it's a bit hard to draw that, like all of space. So people do this, sorry, people do that, and it's wrong, and now I'm perpetuating the myth as well, so please forgive me. The Big Bang isn't too interesting. What is more interesting is after it, the inflationary period, not this sort of inflation, a different sort, and this is the brief period right after the Big Bang that space went from microscopic to macroscopic. So it expanded by a factor of 10 to the power of 26. That's 1 with 26 zeros after it, and it expanded that fast in the first billionth of a billionth of a billionth of a second, which is an insane roller coaster ride, frankly. And at that point in the universe, we essentially have a quark soup. So it's so hot and there's so much energy that nothing can really exist apart from the most basic building blocks of matter. So we have quarks, we have some fermions. If anyone knows what an electron is, that's a fermion. And most of all, we just have light. Billions upon billions of photons, and they're what dictates how the universe is behaving. So we go from inflation, and we fast forward now for 3 minutes. And we get to something called nucleosynthesis. So in the 3 minutes, these quarks have come together. They have formed protons and neutrons, and those will then come together to form atoms. And it takes 3 minutes until the universe gets cool enough that this can happen. Otherwise, before, if they came together, they just get hit by a photon of light, and they smash apart again. So 3 minutes in, it's cool enough that they can start combining, but they don't all combine to get everything that we're used to today. The Big Bang nucleosynthesis only gives us a few elements. So if you start here with protons and neutrons, you can get a few things from them. So you can get deuterium and tritium, and these are hydrogen isotopes. So just add some more neutrons, and then they can go together to form helium, so add another proton, and then you can get some beryllium, some lithium. But by large, you have almost everything here, and just a hint of these guys, right? Almost none of that, because you see the arrow coming down from beryllium, it's not stable. All of it that forms decays to lithium. Half of that then goes back to helium. So the two most stable atoms that we get, hydrogen and helium, make up 99.99% of the universe at that point in time, which is pretty cool. And all the helium that we have today, all the hydrogen, is obviously created there. So moving on, there we go. We get 47,000 years of fire and pain pass, and the universe goes from light-dominated to matter-dominated. And I wanted to talk about this a bit. It's not normally in the public talks that we give because it's slightly technical, but to me it's important because what dominates the universe at various times dictates how the universe evolves. At the start, the universe is dominated by light. There are many more photons than particles of matter. So the light determines the dynamics of the universe. But that changes 47,000 years in, and matter becomes what controls the history of the universe. And the way it works is a little bit technical, so bear with me here. We have two universes in 2D. They're very simple universes. This one is 1 by 1 in size, and it has 8 green particles of matter and 8 photons in blue. And then the universe, as we know, is expanding. So at some point, it looks like this. It doubles in size, so there's 4 times the area. And if we now ask the question, how much stuff is there per unit area, we'll notice that, hey, we've gone from 8 green balls down to roughly 2, right? Because they spread out evenly. The light spreads out evenly too. But you'll notice there's something different with the light, right? It has gone from blue to red. And that's because light is a wave, and it's traveling through space. So if space expands, the light expands with it. And the longer the wavelength is of the light, the less energy it has. So light loses energy simply because A, it goes and fills up all the extra space, just like matter, but it also gets stretched out. And that's a process known as redshift. And I have to introduce it now because it's super important later on. So again, we wait now another 340,000 years. We get to around 380,000 years, and we have something called recombination and decoupling. Before this point in time, the universe is opaque. Light and matter are coupled together. There's a very good example of this, which is if you have a gas, like we do right now, air, you can see through it, right? Because light and the air is not coupled. It's not ionized. So all the atoms have their electrons. And then you take the sun. This is a ball of gas too, but it is ionized. And you'll notice you can't see through the sun, but you can see through air. So this is the difference. The universe, at around this time period, goes from being opaque like the sun, and then it cools down enough that all the atoms take back their electrons, light stops interacting, and the universe suddenly becomes transparent. And at that point in time, the time just before it becomes transparent, and this happens very quickly, the last bit of light that it emitted is what we see here in the background. So this is called the cosmic microwave background. This used to be very, very intense light, but because, remember, space is expanding, as that light has traveled to us, it has been stretched and stretched and stretched so that it's now down in the microwaves. So it's been stretched by a factor of 1,000. But this is interesting, the cosmic microwave background. This is some of the best astronomical science you can do at the moment, and I will definitely come back to this later on. So now we wait for a fair bit. The universe is in this transparent state with a lot of gas, and gravity starts to do its thing. Gas obviously wants to be in equilibrium, right? So gravity wants to pull everything together. Gas doesn't quite want to be squished together, so it resists gravity. If you give it enough time, though, clumps start to form, gravity starts to win, and it pulls down the gas and starts creating stars. So 200 million years in, we get the first stars forming. And I just wanted to have a brief aside, because I find this diagram really fascinating. The reason that stars form, the reason that fusion works, is because if you take two hydrogen atoms and smash them together so that you get a helium atom, you get energy out. And this is exactly how a star works. Gravity crushes all the gas in until the center of the gas cloud is so hot that fusion starts occurring. That fusion releases energy. That heats the gas up even more, so you get more fusion. And because the gas now gets hotter and hotter, that works to balance the gravitational force pulling in. So you have gravity in, fusion pushing out, and hopefully they reach an equilibrium, and that's when you get a star. So stars don't just fuse hydrogen. They fuse a whole bunch of things. They'll fuse helium, lithium, carbon, oxygen, and they'll go up until this zone of maximum stability. And what that means is that if you try and take iron and smash two of them together, you don't get energy out anymore. You have to put energy in. So essentially, if you move from left to right, because you're going up, you're going to get energy out when you fuse the elements together. Now, nuclear bombs and essentially nuclear fission, so the great fission stations, work the opposite way. You start on the right, and then because if you move right to left, you're still going up, that means if you split the atom, it releases energy. So essentially, everything is working its way towards iron because that's where you no longer get energy in or out when you try and tamper with the atom. That's pretty cool. So we had stars at 200 million years, and then we get up to a bit of structure. So we get galaxies starting to form. The stars are coming together, clumping into groups. And what I've got in the background here is an amazing image of the Whirlpool galaxy. Well, that's the Whirlpool galaxy, M51A. And that's M51b. And so this is a companion dwarf galaxy that is getting done over a bit by the Whirlpool galaxy. It's sort of tearing it apart, but that's life. So galaxies form essentially by, initially you get stars. The stars will clump together into stellar clusters or globular clusters, depending on if they have a black hole in the middle. And then those come together too. So this is a little video that NASA made up, and it's essentially a hydrodynamic simulation of the universe as it develops. So they put particles in there and simulate it like a gas, but with lots of gravity. And you can see that galaxies don't form by themselves. Small ones form, and they eat each other. So the Milky Way has had dozens of galaxies come into it and be encapsulated, and you can actually see their remnants in the night sky. If you have a nice little amateur telescope and you look for something called like 47 Tucán, that's a globular cluster. That is the core of a galaxy that the Milky Way ate. The core stays together, and the Milky Way takes everything else and adds it to its own disk, which is cool. At the same time that galaxies are forming, we have larger scale structure. In fact, this is literally called large scale structure. So what you see in the background here are the Millennium simulations. Here's the Eagle simulation. And what you do is, this is a simulation of the universe where you start with mass essentially spread out evenly, and then you let it evolve in time. These are particles of dark matter and regular matter. And you can see that you get structure starting to form. Initially, what was this mostly blank uniform distribution is evolving into what's called the cosmic web, or cosmic filaments. You see a few places now that you have these sort of white outflows. So in the center of the filaments, when you have the most mass, the greatest density, you get galaxies and galaxy clusters starting to form. Within those, you have stars. Some of the stars die, and they die violently in supernova explosions. And those white areas are the supernova ejecta being flung out into space. And it's actually really important they do that, because if we didn't have ejecta from supernova and other dying stars, all we would have to work with in the universe is hydrogen and helium. We get our oxygen, our carbon, and everything else from stars dying and spewing their contents out into the interstellar gas clouds. I just love this simulation too, it's so pretty. Okay, so I'm gonna skip forward 4 billion years because nothing really happens. It's a bit of a boring time. We get to the Milky Way. But fun fact, this is not quite true. Like 5 billion years, so 5 gigayears that I've put here, and I sort of just made that number up. And I did that because 5 billion years is how long it roughly took for the disk in the Milky Way to form. If you find the star clusters in the Milky Way and try and date them, you go all the way back to 200 million years after the Big Bang. Right? There are stars in the Milky Way that formed that were the first generation of stars after the Big Bang itself. So when does the Milky Way begin to exist? It's a bit hard to tell because are we talking about the disk? Are we talking about us? Are we talking about the stars? It's not black and white. So 5 billion years. If anyone asks you that, obviously you have like trivia, and when you go to parties, you want to be the life of the party. Good fact. Okay. Notice the minus sign here. So 4.6 billion years ago, it gets a bit weird when you're talking about things closer to home to keep saying, 8 billion years, and you're like, but how long is that until now? So 4.6 billion years ago, the sun started to form. And when stars start to form, they have what's called a protoplanetary disk. And this is a disk of gas and dust. And the dust ranges from the micrometer size to something, quite hefty. And they essentially form a disk, and then planets grow out of that. Planets like Jupiter grow out of the gas. Planets like Earth don't. They grow out of the dust and the rocks. So here's one of my favorite images of all time too. This is H.L. Tauri. And this is an image from a radio interferometer called ALMA. It's 450 light years away, but we can get this amazing resolution out of it. And if you look right in the center and change your color scheme so you can see it, you get this. This is a disk, a protoplanetary disk of another star. So planets are forming there. And you can see when we run a simulation of it, so this is thanks to a PhD mate of mine, Josh Calcino. He took the very first picture you saw. Running an enormously large simulation on the UQ supercomputers of the protoplanetary disk. And you can see that with these little bodies, so the white dots are put in for your visual aid. They're not actual planets, but they are growing there. And you can see them carving out this dust, carving channels, and the planets in there are growing. And this is exactly how the Earth grew, which is pretty fun. And then obviously, if that's how the Earth grew, the next slide is a fantastic NASA picture of planet Earth. Yeah, I'm going to cop it for that. It's angry emails. Right, so that's Earth. That's Earth. It's fine. But that's essentially a brief history of roughly 14 billion years. And I believe I actually did that under time, so go me. so let's jump into the science part of it. This is the part that I actually care about, and it's the part that isn't normally done in public talks. It's going to get slightly technical, but I've modified all the plots and the figures to get rid of all the axes, because that's normally the main thing that people don't like. Right. So I promised I'll talk about this again, the cosmic microwave background. So here we go. Here we go. OK, that's what we see. That is a projection from the entire night sky, just shrunk down into this oval, right? It's not in one direction. Everywhere you look, you will see the cosmic microwave background. It was actually discovered by accident. They had a microwave detector pointed up at space, and they were just trying to do some baseline tests. And obviously, if there's nothing up there that you're pointing the telescope at, you should get zero signal. And they kept getting this weird, fuzzy signal in. They thought they had some defect in the machine, something was wrong. Maybe someone had a microwave on 10 kilometers over, and the door was leaking a bit. That actually did ruin a bunch of their observations. No, it turns out they were seeing the cosmic microwave background. They just didn't know about it. That's cool. But the interesting thing on this image is how these dots essentially are distributed. So what the dots represent are small patches in the early universe, some that were just a little bit hotter than others, some a little bit colder. So blue, cold, red, hot. And that's simply because after inflation, when you had all this matter and energy in the universe, it wasn't perfectly distributed. Some parts had just a bit more than others, and that's just a fact of quantum mechanics. Quantum mechanics just says sometimes things happen because they can, and you're like, all right then. But what that means is we've got around 0.1% more in some locations than others, right? So this is a tiny difference. So obviously we've subtracted out the mean. And what we want to know is how big are these dots, because that tells us something very important about how the universe evolved early on. So let's actually analyze that image. You get something that looks like this. I'm not going to go into it too much, but the yellow dots are the image decomposed down into data, and the blue line is what we think our cosmology is, our best fit that says there's 70% dark energy and 25% dark matter and 5% of all the normal stuff. That's the blue line. If you turn off dark matter or dark energy, this changes completely. Those peaks go up there, that one drops down, and that shifts to the left or the right. Right? So just from this alone, you could be 100% confident that dark energy and dark matter aren't just a fluke. Right? Has anyone heard of the Higgs boson? That was discovered, and it was discovered at what's called a 5 sigma confidence, and that just means they're 99.99% certain it exists. I can't tell you how certain I am in a percentage, because there are too many nines. I would be here all night. It is absolutely amazing the precision that they've managed to get this to. And it's taken 3 space satellites and 30 years of analysis to get to this point. It's a big effort, but I like it. OK, moving on to the stuff that I actually do myself. Supernova, so standard candles. These are exploding stars. And the one that we care about is called type 1a supernova, because they have this nice property of all being pretty much the same, right? If you have supernova that are all different, you can't really use them. But if they're all the same, then you can get some nifty science out of it. But the way that they work is even more interesting. So you start with binary stars. Binary stars are not an infrequent thing. A significant portion of all the stars in the universe are in binary relationships. So you have 2, and one of them starts to get old, and stars enter their giant phase when they get old. They swell up. But because it's swollen up, the other star, which now has a stronger, it's swollen up so its gravitational hold is weaker, the other star eats the gas, gets heavier. Some of the gas that isn't eaten by the other star gets ejected out into the intergalactic and interstellar dust, and you get a planetary nebula. Roughly looking like that. Thank you, NASA. So that dust is also very important for seeding the next generation of stars, for seeding planets, getting all those heavy elements. But if we go back to the system, the binary system, and this is the double degenerate precursor, you can see that the white star here, so this is what the giant star used to be, is now small but extremely heavy. That's what this dint in space-time is meant to represent, how heavy it is. It's a white dwarf star. It's literally the atoms pushing against each other so close that you can't squeeze them down any further without the atoms themselves collapsing. They are extremely dense, and now this, oh no, oh no. Mate, can we like skip halfway through the video? Just move your mouse. Yeah. Thanks, mate. Yeah. Please stand by. No? Well, let's just admire this absolutely amazing infographic once again. And made by Castro. I'm very delicate about pressing this now. If I do that again, I'm just going to move on. Like, you don't get to see the rest of the video. So I guess fun thing about the white dwarfs here, they are held together by something called electron degeneracy pressure. So electrons don't like being next to each other. So if you take atoms and crush them down, eventually the electrons will say, yeah, no more, we're too close. You can actually crush them down further into something called a neutron star. And that's a bit chaotic and even heavier. Right, so let me try not to screw this one up when it goes back. So, super heavy white dwarf. This star has eaten a lot of gas. It's gotten heavier, so it's burning through its life faster. The heavier a star is, the shorter it lives, right? Because it burns through its reserves much quicker. So we get this, and this star starts to swell up. And as it swells up, it loses the hold it has on its outer layers, and the white dwarf eats them. And that's fine, but you see something's filling up down here, and this is bad. You get to 1.44 solar masses, and at that point, something fun happens. The white dwarf explodes. So essentially, what you have is gravity pulling in on the white dwarf, and all the electrons trying to stay away from each other, pushing out. And that's balanced, but if you keep adding mass, gravity gets stronger and stronger, and eventually it wins. But what happens when it wins? At the core, or just before the whole thing collapses, it gets hotter and hotter. You know, the more you squeeze something, the hotter it gets. And so all the elements, like carbon and oxygen mostly, at the core, well, when it gets hot enough, they start to fuse. And then they release energy. And unlike a star, which maintains equilibrium, it will grow in and out if there's too much fusion, a white dwarf doesn't have that, because it's not supported by gas, it's supported by electrons. The technical explanation is a bit detailed, so I'm just going to leave it there. But what that means is instead of having a controlled fusion reaction, you have a runaway fusion reaction. And a huge chunk of the entire star gets flash fused in about a second into higher elements. And that then increases the temperature, and essentially everything just fuses a crazy amount, and it releases an enormous amount of energy. It tears the star apart. It tears anything close to the star apart. So yeah, hopefully there's not one close by. The good thing too is that these shine for months, right? They shine for around 2 months, so they're actually quite easy to detect. And what we do is we do 3 things. First, we measure the brightness of the supernova. And this is because they're all pretty much the same brightness, because they all explode at around the same mass. They all turn around the same amount of mass into higher elements. They like fuse the same amount, so they release the same amount of energy. So they're all the same brightness. Now, if I held a bulb that emitted a certain amount of light, and I held it close to my eye, it's super bright. If I then move it away, it's less bright for me because the light is spreading out in all directions. So brightness, if we can measure that, essentially tells us one method of how far away the object is. The other thing we do is look at redshift. So redshift, to remind you, is the expansion of light, well, the stretching of light due to the expansion of space. There's another way to think about redshift, and it's the Doppler effect. Everyone has seen clips or been to car races, and as a car shoots past you, you get that meow. What a beautiful effect. But that drop in pitch is because the car's moving away, so the sound that it's emitting gets stretched out. The same thing, you can think about it as the same thing for light. Because the universe is expanding, space is expanding, if we're here and there's a star there, space is stretching, it essentially looks like this star is moving away from us. Not because the star's moving, but because the amount of space between us is increasing. That looks like movement. So you can think about redshift as essentially the Doppler effect for light. The caveat is just that light moves a lot faster than sound, so you need to really be booking it before light looks redshifted. But that gives you this axis, and then the science part comes in on that white line. So we say, hey, if we have this much dark energy and this much dark matter, and they behave in these ways, what line do we get? And you can see, at the moment with supernova cosmology, you get a pretty precise fit, right? This is a nice relationship, and we can exploit that to try and constrain mostly the nature of dark matter. We're trying to do the nature of dark energy too, but we need like 10 times as many supernova. It's a tricky question. Cool. So, gravitational lensing. There are 3 forms of this: microlensing, weak lensing, and strong lensing. I have time constraints, so we're going to talk about the coolest one of them only, which is strong lensing. And strong lensing is perfectly explained by this helpful little video. And so you have a background, spiral galaxy in blue, emitting light in all directions, but we're only going to show 3 directions here. And there's this galaxy cluster in the middle. And because the galaxy clusters bend space and time, because they're so heavy, the light that's traveling through them or by them gets bent as well. And because of that, when it reaches Earth, we don't just see one image of that, we see 1, 2, 3 images of that background galaxy in different positions on the sky. So a 2D analogy for this is to imagine if the stage here was a trampoline, and I wanted to roll a ball directly across from me. If the stage is flat, if there's nothing on it, I just roll it in a line, and that's how we normally perceive light. It comes to us straight, right? It doesn't bend at all. If someone put a mass in the middle of it, like a bowling ball, I then have 2 options. I can roll the ball to the left, and it will curve to the right, or I can roll a ball to the right and curve to the left. So you can do the same thing in 3 dimensions, but instead of having 2 options, you now have a circle, which looks a bit like this. What this is a blue spiral galaxy directly, well, almost directly. You can see it's not perfect because it's not a complete circle, but it's almost perfectly behind this red giant elliptical galaxy. And this is really cool. This is called an Einstein ring, and we've actually found a whole bunch of them simply because there are so many galaxies. The interesting thing, though, is the diameter of this ring tells us about the mass in that galaxy. If there was more mass and more curvature, the ring would be bigger. So what you can do is you can take really nice images from Hubble, and you can then identify strongly lensed events. So those 4 blue things are the same object, but the light has traveled in 4 different paths to get to our telescopes. Same thing with these ones here. They're the same thing. And if we find enough of these strongly lensed galaxies and images, we can then use that and a very big supercomputer to try and say, hey, how must the mass lie? So if you get these images here and they're distorted in this way, where must the mass be to produce that image? So you can do that, and then once you have your mass map, that tells you about cosmology. Remember, dark matter is gravitational. It pulls things together. You have more dark matter, you have more clumpiness, more structure, more growth in the universe. Dark energy is anti-gravity, pushes everything apart. So if you have more dark energy, you get less growth of structure. Everything's further apart. So that tells you what you should expect to see in the mass map. So that's really cool. And by itself, this also would confirm dark energy or dark matter. Another one that I've personally done is using large-scale structure. So we talked about, you saw that simulation of the universe evolving from essentially a uniform distribution down to galaxy clumps in the cosmic filament. Well, we can try and look for those in our surveys. So what you see here is an animation I made that shows around 7 or so galaxy surveys. The one at the top in purple is an American one called the Sloan Digital Sky Survey, and then pretty much everything else that I decided to put on the plot are Australian-based surveys because I'm a little bit biased. So this one here, the one in yellow right at the center, is 6DF. You can see where the Milky Way lies if you look at 6DF and SDSS as it revolves around, because you can't observe through the Milky Way galaxy. It's filled with dust and stars and other trash that we don't care about if you're doing cosmology. You care about it if you're doing other things in astrophysics, right? But we don't. And so you can see we've cut the galaxy out. But you'll also notice that by looking at the position of all these galaxies, we can see structure starting to emerge. And that's us tracing out these cosmic filaments. So the way that you do that formally is you measure a bunch of galaxies. This is 6DF. You then say, hey, how far away is every galaxy to every other galaxy? We won't go into the details there. But you're looking for a peak, this little bump. The size of that bump, the shape of that bump, its location, all tell you about the earliest evolution of the universe, because this bump comes from those cold and hot spots that you saw in the cosmic microwave background. Those hot spots represent spots with more matter. More matter means more gravity means more stuff forms. So those spots in the very early universe are what collapse and form all these huge galaxy clusters. So by tracing the galaxy clusters, we can link the universe from as it is right now to how it was 300,000 years after the Big Bang, which is pretty cool, pretty cool. Right, and one of the last things that I think I should touch on is galaxy interaction. And this is the last one because it's not strictly speaking cosmology. Everything else I've talked about is cosmology, but cosmology means we're looking at the largest scales in the universe. It's evolution over time. It's the beginning, its fate, and how it's going to die, right? Heat death, if you want a spoiler. So this isn't. This is just looking at stuff closer to home and doing other science. But it still tells you about dark energy and dark matter, which is fantastic. Here is the Triangulum galaxy. And we can stick some fancy instruments like spectrographs onto the galaxy, and it tells us how fast the galaxy is spinning at different locations. And what we expected is if we counted up all the mass in the galaxy that we can see from stars and gas, we expect the rotation curve, so that's its velocity as a function of radius, to drop out like this. This is sort of intuitive, right? If you imagine you're trying to spin something around your head, if you have a short string, you have to spin it really fast. If you have a longer string, you can spin it slower, right? And so we expected to see that in other galaxies. The further away you are, the longer your orbit is, just like in the solar system, right? If you go out to Neptune, it doesn't orbit at the same period of the Earth. It takes much longer because it's further away. And yet we see this. We see the further away you go, the faster you orbit, which makes no sense given most of the stuff in the galaxy is at the middle of it. So there must be stuff outside of the middle, and lots of it, because look at that distance, that is causing everything to move faster than we expect. So this was actually the first observational evidence of dark matter that we have, and this is thanks to Vera Rubin. She passed away last year, and we're all a bit sad that she didn't manage to get a Nobel Prize before she passed. But that's all right. So the second one that I wanted to talk about is called the bullet cluster. So these are two clusters of galaxies that have passed through each other. They have collided, but because space is so big and empty, the clusters themselves don't care. They just keep going. Stars don't hit each other because they're too small, but gas hits itself. So stars are very dense objects, right? Gas is not dense. It sort of spreads out everywhere. So if you have two clusters and they try and pass through itself, all the stars shoot past, but all the gas hits itself and gets stuck in the middle. And you can see gas in space if you point an X-ray telescope at it. So that's what you see in red, all the gas. Now, in a galaxy, stars make up around 10% of all the visible mass, and 90% of it is stuck in gas. So if all the gas is here, we expect most of the mass to be there, right? And like if dark energy doesn't exist. But what we can do is use another trick of gravitational lensing called weak lensing, and that allows us to also map out where the mass must be. And NASA's plotted that in blue. And you'll notice something very fun. You have cluster, cluster, all the baryonic matter, but all the mass is still out there. And so this is mass that can't be gas, it can't be particles, or it would have collided. It can't be stars because we can count the stars up. And if you'll notice that the blue is between the galaxies, not just at the galaxies. So it's something there that emits absolutely no light and doesn't interact with anything else except for gravity. So this is like my favorite piece of evidence for dark matter because there is literally no other explanation that we have to explain anything remotely like that. So that's fine. But even though it's my favorite piece, it doesn't mean there isn't more. There's so much more that we can do. So there's a bunch of people at UQ working on something called reverberation mapping. So what you do is you look at quasars, and quasars are supermassive black holes that are accreting matter. So they're sucking matter in the early universe, and they have accretion disks. If you've seen Interstellar, you've seen something similar. But what happens is as the gas gets sucked into the black hole, it rubs against itself. And just like when you rub your hands together and they get hot, so too does the gas get hot when it tries to spiral into the black hole. And it gets so hot, it glows. Quasars are essentially the brightest things in the universe just because of friction. The amount of energy that the mass loses as it falls in is around 10% of its total light mass. So let's just say it's 100 times more efficient than nuclear bombs at releasing mass, and it's just friction, which is scary. But fun. But that's not powerful at all compared to gravitational waves. So last year, the Nobel Prize in Physics was awarded to LIGO. And they got the Nobel Prize because they observed gravitational waves, and these were a prediction of Einstein's from general relativity. And what he predicted was that as two bodies orbit each other, they slowly start to decay because they're losing energy into these waves rippling out in space-time. So just imagine you're on a boat going somewhere. You have wake. It's a similar principle, but with space instead of water. And LIGO managed to observe two black holes spiraling in faster and faster until they merged together. The fun fact was, in the 3 seconds it took those black holes to merge, they released so much energy in the form of gravitational waves that they outshone every star in every galaxy in the entire observable universe combined. So I would have really hated to be close to that when they merged because we felt it and we were a billion light years away. So it should be fun. And these happen all the time too. How great is that? The third one that I have time for is just a brief touch on particle detectors. You don't have to go into space to study space. In fact, these guys went into a mine and then went down as deep as they could go, tunneled it out, put a bunch of these gold photo detectors, so these are just cameras, and then they filled it with 50,000 tons of water, as you do. And the principle here is that there are particles called neutrinos that are streaming through the Earth all the time, and they normally never interact with anything. They go straight through you, but every now and then they interact. They hit an electron or they hit a proton. And the idea here is if they hit an electron in the water, they give that electron all their energy, right? They get, essentially, just think of it like when you're playing pool. You hit the electron flies out. And if you hit the electron hard enough, the electron can move through the water faster than the speed of light can move through the water. Not faster than the speed of light in a vacuum, but because light slows down in water, the electron can exceed that speed. And when that happens, you get a form of radiation, Cherenkov radiation, I think that's it. If you've seen videos or movies of a nuclear reactor where they turn the button on and the water suddenly starts glowing blue, it's that reaction. And if you haven't seen videos of that, you definitely need to go on YouTube when you get home because it's super cool. But they essentially wait for those flashes of blue, that radiation, and they observe that to try and figure out where are these neutrinos coming from, what are their properties, and what can we learn from them. So that's super interesting. But even with all those probes, dark matter and dark energy aren't solved questions. Otherwise, you probably wouldn't be here. You'd have just read it on Wikipedia. So what is dark matter? Currently, the leading candidate is a subatomic particle. So there are subatomic particles that don't really interact much at all, like a neutrino, go straight through the planet, but they have mass. So perhaps dark matter is a subatomic particle that's much heavier than a neutrino, so it moves much more slowly, and we just haven't been able to find it yet. However, that's not looking too good. So maybe it's massive objects. For example, so subatomic particles, they're called WIMPs, weakly interacting massive particles. And then just for fun, massive objects are called MACHOs, so it's MACHOs versus WIMPs. And that's massive astrophysical compact halo object, which in English is just a bunch of small or large black holes throughout the universe. And it's hard to see black holes, so maybe it's just them adding their gravity. However, we've looked for them, and you should be able to detect them, and we can't find them. So that's not looking good either. So maybe we got gravity wrong. And when I say we, I mean Einstein. This is obviously his fault. He didn't quite get GR right, and we're still paying the price 100 years later. But if you try modifying general relativity, if you tweak the numbers, you add a field there, change this number there, nothing works. Nothing works, because dark matter has to work on the scale of a galaxy for the rotation curves, all the way up to the scale of the entire universe with a cosmic microwave background. And when you tweak GR, you can generally tweak the small things or the big things, but we haven't found a way of tweaking everything so that it looks just like what we want, that we can experimentally tell apart from if we didn't tweak it at all. So what is dark matter? That's a great question. But what could dark energy be? And this is the one that I like more because this has a higher chance of being something even weirder. New physics is always good, right? When they announced that they discovered the Higgs boson, and they got the Nobel Prize for that, this LHC, it was very disappointing. Because we didn't want them to discover the Higgs boson because it was predicted. So if they discovered the Higgs, it means that the boring standard theory of everything is correct, at least we think it's correct, And how dull is that? Like, wouldn't it have been better if they couldn't find it, and that lets us know that our standard theory is wrong somehow, and there must be unexplained and undiscovered physics, and we can go out and find it? No, they just found the Higgs boson. So hopefully it's something even weirder. Hopefully I figure out what it is, fingers crossed. But hopefully, well, potentially, maybe we just stuffed up gravity too. Maybe there's a way of fixing general relativity such that dark matter and dark energy are explained. Doesn't look too likely. Sorry, that's the brief summary of many nails in the coffin for that. But the one that has the most promise at the moment is vacuum energy. And this is what Einstein accidentally proposed. In the initial theory of general relativity, the universe was static. But if you have a static, as in it's not expanding, but if you have a universe that's not expanding with matter in it, which has gravity, it then collapses and crushes itself. So that's bad. So Einstein was like, oh, well, if I add this number at the end, that's a repulsive force, so the universe is expanding and we get to exist. He got the number wrong because he was trying to balance it so the universe was barely expanding, and we now know that the expansion is accelerating. All that means is if we make that number a little bit bigger. The one issue is we don't have a physical justification for that number. If space-time itself has energy, that is a theory of quantum mechanics, if we had a proper quantum theory of gravity. So cool. We sort of have some potentials, so you can do all the math, and you can say, hey, under our current understanding of quantum mechanics, how much energy should there be in the vacuum? And you get a number, and then you say, hey, looking at our dark energy and the expansion of the universe, what should that number be? And they disagree. They disagree a lot. It's called the vacuum catastrophe, and it is literally the worst prediction in theoretical physics ever. The numbers are off by 120 orders of magnitude. That's a lot. There is no way for me to explain how bad that prediction is. I could say that it means that you think the size of the observable universe is less than the size of an electron, but you're not even halfway there to how wrong that is. So if someone can figure that out, that's a Nobel Prize. We've been trying for around 30, 35 years. No one's done it soon. We've managed to get 120 orders of magnitude down to 60, which is still roughly 60 too much. So hopefully soon someone can get it to be the exact number, and then we'll all just retire. That'll be good. So I guess to summarize then, what is dark matter? We don't know. And then what is dark energy? We also don't know that one. That's fine. And so I guess that means I hope I've answered all your questions. Yeah. Thanks, guys.
Thank you, Sam. I think we're obviously clearly done for the night. No need to go on for questions afterwards. But just in case, if you have some questions for Sam, if you could write them down or start tweeting them now, and we'll come around and collect those questions, wave them in the air, and we'll come around and collect them. While you're doing that, and while Sam is catching his breath after that incredibly exciting talk, we do have one more BrisScience talk for the year, and that is next month on the 3rd of December. And we've got Professor Philip Hugenholtz, who is talking about the mighty microbiome. So all the organisms that live inside us that possibly make up more cells than we do, if we're not actually the organisms anyway. So it should be a really exciting talk and a great way to round up the year. So make sure you come along to that. Also, of course, if this is your first time here tonight, if you could hop on the website, you can find us on Facebook and our website, sign up to a mailing list and get all the information there. All right, going to go to questions first. Let's jump to Twitter while those guys are still collecting theirs. And Twitter has broken. This is fantastic. Yes. Give me 1 sec here, 1 sec here. Okay, the top tweet is about a different sort of vacuum catastrophe, which involves a Roomba and cat vomit. But we're going to move on from that to the...
No, I like that one.
Okay, so you can join me on stage, Sam. And, oh, fantastic, thank you. Ooh. Right, okay, so the first question is from Twitter, and it's from PK, who asks, what happens to a neutrino after it's lost all its energy in a collision?
Becomes sad. Neutrinos can be absorbed. So if they lack their energy, they can be absorbed and turned into kinetic energy. You can get things like if you have a free neutron, just in space, it's unstable, and it will decay into a proton, an electron, and an electron neutrino. So neutrinos can come and go in and out of existence. That's totally fine.
Excellent. Okay, next question is, what was the universe like 15 billion years ago? That is before the Big Bang, perhaps 1 billion years before the Big Bang.
Well, it's a hard question to answer because I don't think it makes sense. Space and time is created with the Big Bang, right? So to ask what happened before the Big Bang is to, for example, ask what is north of the North Pole, right? Once you're at the North Pole, you can't go more north, so you can't really ask what's north of it. It is just north. So what is before the Big Bang? Well, if time is a property like that was created with the Big Bang, there is no before.
Good answer. I hope that we had a follow-up question, which was what is outside the universe? Can anything outside the universe influence us?
It depends how you define the universe. If it's everything, then there can't be an outside. But a lot of people think that the universe has an edge, or that it's expanding into something. When the universe is expanding, it's not expanding into anything, just space itself is growing. Imagine you're just zooming in and out of Google Maps. Google Maps isn't like expanding somewhere in the background, you're just zooming in. That's a better analogy for expansion. And as to an edge, it has a sort of edge in the sense that we can see an edge because we're at one specific spot in the universe, and we can only see things that the photons have had enough time to travel to us, right? So beyond that point, there's still stuff, we just can't see it. So the universe is infinite, even if the observable universe isn't. Yeah.
Great.
Check back in 30 years, mate, yeah.
We're going to have problem solving this one first.
Yeah, no idea.
Question is, those two black holes that collided, what would have happened if they had been a few light years away instead of a billion?
Fun times. Hopefully not too much. So unlike a supernova explosion, which emits ejecta, so it throws particles at you, black hole mergers, and the same for neutron star mergers, simply distort space-time. So it's not like you're getting hit with anything, you're just sort of getting squeezed weirdly. As to its actual effect, I would have to sit down and think about that because I think the Earth would survive? Maybe? Not sure.
Okay, next question. What do you think the next big discovery will be in your field?
Ooh, hopefully mine. No, it's interesting. Everyone is trying to hunt for anything that it could be. So what we're trying to, when we say it might be WIMPs, everyone's trying to create particle detectors to search for a new version of WIMPs. And we keep getting no, 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 no. There's a few promising things. For example, axions are a potential subatomic particle which could make up dark matter, but we don't have the ability to detect them yet. I think the most interesting development in science is gravitational wave science. So now that we can have multiple gravitational wave detectors set up, when we detect events, we can triangulate their position in space. And then you stick a telescope on them, and you essentially follow it up. The beautiful thing with gravitational waves is that they're almost perfect, in the sense where if you get light, there's gas in space, there's dust in space, the light gets bounced off that, absorbed, it gets screwed up. But gravitational waves pass through everything. So that's where I think the next big discovery will come from. We'll see.
Okay, slightly, that's a big question, going down to a little bit more detail. Does the makeup of the initial gases of a star affect the brightness of the supernova or its spectrum?
Yes to both. There are many forms of supernova, so type 1a is the one that we care about mostly because they're the ones that are all the same brightness. There's type 1b, type 1bc, type 2, type 2p, type 2n, a whole bunch, and that's all determined by the composition of the star. So whether or not there's hydrogen shells left, helium shells, silicon, iron, all that stuff, magnesium, will determine exactly how the supernova goes off and what it looks like. Yeah.
So there's a follow-up question, which is, perhaps later, how do we know that all supernovae are the same for those standard candles?
Right. Mostly because type 1As only happen under a specific circumstance, right? That 1.44 solar mass, only for specific stars. That's why we only use type 1As. There would be type 1Bs and type 1BCs, which are similar, but we essentially prune them out. We observe the supernova, and then we make sure all its features match, that it has the peak there and that there, and then we chuck out the rest of the data that doesn't match. So essentially, we have a lot of them, and we only take the best ones. That's how we make sure they're standard.
Okay. You got time for a couple more questions?
Oh, yeah, mate.
Great. All right. So this, a little bit of Steve Irwin there. I like it. So jump on a galaxy and catch it. So, BrisScience. So this question is, how long does it take the Milky Way to rotate?
Depends where in the Milky Way you are. If you're right by the galaxy, so you can be done in 20 years. There are stars that we can observe orbiting the supermassive black hole in the center of the Milky Way, which is Sagittarius A star. And you can see them being flung around by the supermassive black hole at, frankly, ludicrous speeds. And then you go out to where we are, around 8 kiloparsecs away from the center, and it takes us several 100 million years. But that's fine. You can go out further. It'll take longer. It all depends where you are in the galaxy.
All right. One more question for you. If budget were no option,
oh, yeah,
and you had no constraints, I'm adding that bit in, you had no constraints, what experiment would you want to perform?
Ooh, so many. I would absolutely love a telescope on the moon. Because you can't build big telescopes and put them in space. They're too expensive. We have Hubble, and that cost a lot of money. But it's really hard to get a big thing in space because you have to put it up there. You can make really big telescopes on Earth, but then you have the pesky atmosphere that gets in the way and ruins all the light coming through. If we could build something on the moon, big telescopes, no atmosphere, be mint. Make it happen.
We do actually have a hat outside, so we'll be collecting funds for Sam's new telescope. Please, a huge round of applause for Sam Hinton, a fantastic presentation tonight.
Oh, no.
I'll see you all back here next month for more BrisScience. Join us for food and drink. Sam Hinton, everybody.